Welcome everybody to the first lecture on advanced quantum physics for this semester. Before we will start with the main topics that we want to discuss during this lecture and others, I would like to give a brief overview of quantum mechanics and where we came from, why it was introduced, up to the introduction of the Dirac equation. And actually, when we think of the reasons why we started to introduce quantum mechanics and replace the classical mechanics by quantum mechanics, then a lot of this has to do with observations people made in spectroscopy. And that goes back to the early days when Newton started to look at the spectrum of sunlight with the use of prisms. If you look at these type of spectra, then we see that we have discrete absorption lines in these spectra. And not only if you look at the emission of a dilute gas, you see these discrete absorption lines. If you heat a similar gas, then you see that they start to emit at discrete frequencies photons. Now, for people in the 18 or 1700s, this must have been very weird, because classical mechanics actually is always continuous. Any particle can have any amount of energy, and now all of a sudden you see that only discrete amount of energies are available and allowed. Now this has been widely investigated, for example in the alkali metals, where you see different groups of absorption lines grouped together and there are relations between them. And some of these absorption lines are diffuse. Some of them are very sharp, so some of them show, well, they're not so sharp. And actually we can group them according to diffuse and sharp lines. And what people found in the alkali metals is that when you heat them, then the S electron actually goes into the P shell, and now it can decay, and by the decay it will emit a photon. And you can either decay back into the S shell, which gives you a sharp line, or you can decay back into the D shell, which then gives you diffuse lines. And this is why till date we still call an angular momentum of 0s and an angular momentum of 2d, and the angular momentum of 1 is called P from principle, because that's the shell in which you excite at first. And then a bit later people found that you had another set of series of spectral lines, and instead of calling this yet another series, they call this a fundamental set. And therefore they said, well, these are the fundamental spectral lines. There's nothing fundamental about an angular momentum of 3, but that's where the name comes from. Now, all these spectra and all these different lines with different properties, people then slowly started to put into tables, and we have different series. And of course, we can also understand nowadays why a decay back into an S shell is sharp and a decay back into a P shell is not, because decay back in the D shell is not sharp, because the D shell is split by spin-orbit coupling. You have more than one state, and therefore if you don't have enough resolution to resolve all of this, it looks like a diffuse line. With higher resolution, people started to find that these spectral lines are still sharp, but just not one of them. And then in magnetic fields they split even further, and you have the Zeeman effect, which then led to the introduction of spin into the systems. So we have this discrete set of absorption lines that nicely follow certain regularities with all these different series that were detected and known. Then Rydberg, working on numerology, started to find a very simple formula to basically cast all these spectral lines into a simple formula, of course still without any understanding of where it comes from. And that's where Erwin Schrödinger started to do his research. Actually, if you're able to read German, it's still a very nice paper to read. And he said, well, if we look at classical physics, then there basically the dynamics is described by a differential equation. We have the Newton equations that tell you that the acceleration is a force times the mass, so that is the second derivative of the position. So we have differential equations that tell you how particles move into time and space. So he was looking for a similar differential equation that now describes quantum mechanics. And for this we can describe the particles by wave functions. You act on that wave function, and we're looking for a differential equation that then describes these particles. And the nice thing is, if you have a differential equation with side conditions, then this can give rise to discrete solutions. So there is an option to have discrete solutions for such type of differential equations. And the differential equation that he found is basically this one that we see here, the Schrödinger equation. We have the kinetic energy given by the second derivative in space, the potential energy, and then for several particles we have a Coulomb interaction between them. And then of course this acts on a wave function, and the Hamiltonian acting on the wave function is equal to the time derivative of this wave function. We now can compare the classical picture to the quantum picture, and in a classical picture the state or the microstate of a material is described by all positions of the particle and all momenta of the particle, whereas a quantum state, the microstate, is described by the wave function of a particle, which assigns a complex number to all coordinates of the particles as a function of time. And for a single particle we actually can expand our wave function on a basis. So we choose a linear set of independent functions, and then our function is given as a vector on this basis, which is a vector in a complex Hilbert space. So we can actually define our states by vectors in complex Hilbert spaces. This is just linear algebra and the mathematics behind linear algebra. So this can be done in principle for any set of functions that we have. And especially this can be done in quantum mechanics. And it's very powerful when we have linear differential equations describing the dynamics of the system. Now for multiple particles, we can make product functions of the wave functions of single particles, but we have to realize that for fermions we have to antisymmetrize the wave function. So we have an antisymmetrized wave function, and we can write antisymmetrized wave functions as Slater determinants. So we have a determinant of an n-particle wave function. That also means that for n particles we have n faculty terms in this wave function. So if you want to calculate matrix elements between n2 n-particle wave function, you have n faculty square integrals that you have to solve. They're all very related, and we can simplify the mathematics by using different notation, namely the notation of second quantization. But in principle, if you think of wave functions, this is the number of integrals that you have to solve. So it's becoming very quickly very unpractical. For an element like gold, we have more than 10 to the 100 elements in this determinant. Now single Slater determinants are still not general states that we have in a many-body system. These single Slater determinants define a basis, and by taking all possible single Slater determinants and a vector on that basis, we actually can describe true many-particle states. When you have entanglement, when you want to make superpositions of two different states, then this is exactly what you need, that you have to write your wave function as a sum over different single Slater determinant states. And now these vectors in this Hilbert space are actually describing your true many-body physics. So we have these two different ways to represent a state in the classical picture by a position and a momentum vector, and in the quantum picture by a wave function. And then of course the norm square of the wave function gives you the density or the intensity that you have on a certain point in space. Just like for the electromagnetic field, the norm square of the electromagnetic field gives you the energy density that you have at that point in space. So in a classical picture, the dynamics is given by the Newton equations or the Maxwell equations if you have electromagnetical fields, and then the Einstein equations if you want to make things relativistic. In the quantum picture, the dynamics is given by the Schrödinger equation or the Dirac equation if you want to include the relativistic effects or quantum electrodynamics when you want to truly include the full interaction between the electromagnetic fields and electrons. So this is what Schrödinger introduced as his equation. And when he introduced his equation, there were two problems with this equation that were also very well realized. Even by Schrödinger himself, he tried to solve this. And the first problem is that these equations do not include the spin of an electron. You basically have to add this by hand. And the second problem with this equation is that they are not Lorentz invariant. It's basically a classical equation and not a relativistic equation. So Dirac tried to work on this, and in his words, when he basically a year after the introduction of the Schrödinger equation introduced his equation, he said, well, this is a nice equation, we have now the new quantum mechanics, but it doesn't agree with experiment, which is a bit harsh because the Schrödinger equation for the hydrogen atom actually agrees reasonably well with experiment. I mean, it describes a lot of things, but indeed, in terms of duplex phenomena, we don't have spin. And it was very well known that we have spin. If you look at thermodynamics, you see that we have to have two states. If you look at the periodic table, you see that you have two elements per angular momentum state. If you look in spectroscopy at the Zeeman effect, you see that your states split in the magnetic field. So it was very well known that the electrons needed to have an angular momenta and that you have these two states for the angular momentum of the spin of the electron. And that's why Gauss-Smit and Uhlenbeck introduced the spin of the electron as an angular momentum of a half, such that you can have spin up and spin down, a twofold degenerate state, thereby giving you the duplex phenomena. So Dirac said, well, if we now can find a relativistic equation that immediately also includes spin, that would be very nice. And of course he wrote this abstract after he found his equation. So let's see how we can try to derive, or not really derive, but rationalize the ideas that Dirac had, how he came to his equations. And classically we have the energy momentum dispersion, that the energy of a particle is a half mv squared. And we can basically write this also with the momentum of the particle, where the energy is 1 over 2m times p squared. Then, in order to get to Schrödinger's equation, we replace the energy by the time derivative operator, the momentum by the gradient or the space derivative operator, and we let the operators act on a wave function, whereby the wave function now describes the state of a system. And that's the Schrödinger equation. We can also try this for the relativistic energy momentum dispersion. For a particle in rest, this is mc squared. For a particle with finite momentum, this is m squared c to the fourth, c squared p squared, and that then is not equal to e, but e squared. So we have a quadratic relation for the energy and a quadratic relation for the momentum. We can still replace the energy by a time derivative operator, the momentum by a space derivative operator or the gradient, and this is the equation that we find. And this equation actually is known as the Klein-Gordon equation, where Klein and Gordon basically both independently published this equation and used it to have a look at Compton scattering of the electrons. Now, the Klein-Gordon equation doesn't describe the physics of the hydrogen atom. If you do this equation for the hydrogen atom, then you will find that the relativistic corrections are not in agreement with experiment, and the Klein-Gordon equation still doesn't include the spin of the electrons. And actually the Klein-Gordon equation can be found in the notes of Schrödinger, where he basically started with the relativistic case. Then he noticed that this does not give the correct relativistic corrections for the hydrogen atom, and therefore discarded this equation and published then the non-relativistic limits of quantum mechanics. He actually worked very hard to find a relativistic equation, but didn't manage. So back to the idea that Dirac has. We have to look at an equation that can include the spin and becomes Lorentz invariant. And Gauss-Smit and Uhlenbeck already showed that we have a spin of angular momentum a half. And then, as Dirac also wrote, Pauli and Darwin basically made an equation where this was added to the Schrödinger equation in a relative ad hoc but working way compared to experiment. So let's have a look on the equations that Pauli and Darwin proposed. And Pauli and Darwin said, well, when the electron is a spin 1/2 particle, then we should not have one complex number for each point in space, or for each coordinate of the electron, But we need two complex numbers. One related to the prefactor of a basis vector with spin up, and one related to the coefficient for a basis state with spin down. And then if you have an electron with spin up, it's basically the vector 1, 0. If it's an electron with spin down, it's 0, 1. If we put the spin in the x direction, we have the vector square root of half, square root of half. If you want to put the spin in the y direction, you have the vector square root of half plus I square root of half, or square root of half I square root of half for the up and down components. And we can now write the Schrödinger equation acting on a vector. But actually, when we think of quantum mechanics, when our basis states are vectors, we do not write the Schrödinger equation as a scalar, but actually we turn it into a matrix. We have always matrix for operators. So our Schrödinger equation has to become a matrix, and of course the matrix here is diagonal because the kinetic energy or the time evolution of a spin-up particle or a spin-down particle are completely equivalent. The original Schrödinger equation did not include spin in that sense. Now we can add magnetic fields, and magnetic fields acting on the orbital angular momentum is the same for spin up or spin down. So again, this is an identity matrix, but the magnetic field interacting with the spin of an electron now becomes off diagonal because the x and the y component are actually given by the Pauli matrices, and these are purely off diagonal on the basis of spin up and spin down quantized in the z direction. So this is now a matrix representation of the Schrödinger equation, including spin by Pauli and Darwin. And of course we can also add spin-orbit coupling, where the electron, when it moves around the nucleus, we can basically turn the picture around. The electron sits, the nucleus is moving around the electron, and when the nucleus moves, for the electron it looks like a moving charge, thereby it produces a magnetic field, and that magnetic field then interacts with the spin of the electron, and that is exactly this coupling between the electron angular momenta and the spin of the electron. And then again with a prefactor, and the spin of the electron is here given by the Pauli matrices, and therefore we have the Lz component on the diagonal, the x and the y component on the off diagonal. And G and sigma are basically experimentally determined parameters in Pauli and Darwin's equation, where the G, the geometric ratio, is actually first determined by Einstein. Einstein did his measurements and he found that G was 1 in his measurements, most probably because that would be the most natural number to observe. We of course now very well know that G is 2 or very close to 2. So sometimes it's good to write down what you expect and then make sure that you don't see what you expect because that's the thing you expect, but still be honest in when you do your experiment. So that's the point where Dirac was basically sitting. He knew that we have the energy momentum dispersion relations, that if you replace them in the non-relativistic limit with the operators of the time and space derivative for energy and momenta, you get the Schrödinger equation that reasonably worked. But if you do that for the quadratic equation, you get a Klein-Gordon equation which does not work. So he said, well, maybe we should look for a linear equation, just like the Schrödinger equation is. So I don't want an equation for E square, I want an equation for the energy in terms of momentum. So we can write the energy as a function of momentum and the mass. And now we require that the square of this function becomes p square c square m square c to the fourth to reproduce the relativistic energy momentum relations. Then this sets some requirements on alpha and beta, and actually the requirements on alpha and beta are that they anti-commute, so alpha I alpha j plus alpha j alpha I is 2 delta ij, and the same for beta. So the product of beta with alpha has to be 0 for the anti-commuter, and beta square has to be the identity matrix. This is obviously not possible for complex numbers, because complex numbers multiplied with itself, or there's only one complex number set that squared is 1, that is e to the I theta, and that multiplied by another e to the I theta is never going to give you the delta function. So for complex numbers this is not possible. But we've already seen from Pauli and Darwin that in our Schrödinger equation the Hamiltonian actually should be a matrix. And for this to be a matrix, the alphas have to be matrices. So we're not looking for complex numbers that fulfill these equations, but we look for matrices. And now we can look for 2 by 2 matrices, and then we have the Pauli matrices in there. And what we saw is that you indeed have to add the Pauli matrices to get the equations of Darwin and Pauli. So can we do this when our wave vector is a 2-component vector on the space of spin, and our Pauli matrices or our alpha matrices are 2 by 2 matrices with the components for up and down. Now if you look at the requirements, then we can find 2 by 2 matrices that fulfill these requirements, and actually these are the Pauli matrices. So if you look at sigma x, sigma y and sigma z, or sigma 1, 2 and 3, then they nicely fulfill these relations. Now the Hamiltonian has to be Hermitian, so our matrices have to be Hermitian. And if you look at how many Hermitian matrices there are for 2 by 2 matrices, that is 4. So we have the 3 Pauli matrices, and then the 4th matrix is the identity matrix. But the identity matrix does not fulfill these equations, because the identity matrix times the Pauli matrix is the Pauli matrix itself. So it does not give you 0 or a delta function. So we only have 3 matrices, and we need 4. 3 for the momentum, 1 for the component in front of mc squared, the rest mass. So what did Dirac do? Instead of giving up, he said, well, then we need to go to higher dimensions for our alpha matrices, because then I have more options. And indeed, for 4 by 4 matrices, we can nicely fulfill these equations. And that's the solution that Dirac then has. His wave function now has 4 components, a large component and a small component with spin up and spin down. And then the alpha matrices are 4 by 4 matrices, where it's basically on the off diagonal for alpha 1, 2 and 3 we have the Pauli matrices, and alpha 4 or beta is the identity matrix, where the part acting within the large space is plus and the part acting in the small space is minus. We can now look at the eigenstates of the Dirac Hamiltonian on this basis, and if the momentum is 0, we can easily write down what our eigenstates are, and these are basically the basis states. So the eigenstate of the Dirac equation, where the time derivative of the wave function is the Dirac Hamiltonian times the wave function, then becomes a vector, and we have the first component is the electron with the spin up, the second component is the electron with spin down, and now of course we have 2 more components, and they relate to the positron with spin up and the positron with spin down. And then with finite momentum we can have a look at solutions where the momentum is parallel to the spin, and then we see that the spin up of the large component get an admixture of the spin up the small component. I did not normalize my wave function in this case, just to make it a bit smaller, and we see that the momentum dependence or the position dependence basically is the same as we have for the non-relativistic case. We get plane waves that can propagate, and either with spin up or spin down for the electron. Maybe we have the large component and the small component. And we can do the same for the case where the spin is perpendicular to the direction of motion, and then we see that the large component with spin up gets an admixture of the small component with spin down. So this basically takes care of all the Lorentz boosts that we have for the electromagnetic interactions between particles and the spin related to the magnetic field and the electric field that your particles produce. If we look at the size of the large component and the small component for our electrons as a function of the kinetic energy that our particle has, or better said as a function of the total energy minus the rest mass energy, then you see that when the momentum is 0, the energy is the rest mass energy, the large component is 0, and then when you accelerate the particle, also the small components start to admix to this wave function. Well, instead of looking at the components themselves, we can look at the square of the component. And then you nicely see that you get a symmetric plot where, of course, the large component squared plus the small component square is normalized, is equal to 1. Our wave functions are still normalized. And then, of course, in this case, it means that the norm of the vector has to be 1. Now, if we zoom in from 0 to 100 eV for the kinetic energy, which is for our daily life still a large number, kinetic energy of particles at 300 Kelvin is 30 millieV, energy of the sunlight is of the order of electron volt, the binding energy of an electron in a hydrogen atom is a Rydberg, so 13.6 electron volt. So we're here at high energies where electrons basically would not bind to the atoms anymore. And you see that the large component is basically 1 and the small component is basically 0. If we zoom in and look at the small component, or 1 minus the large component, then you see that they are basically the same. I look at the squares of them, such that the sum of them is 1, and that the small component is less than 1 or 0.1 promille of the large component in its norm squared, up to kinetic energies of 100 electron volt. That, of course, asks to do perturbation theory. Because, well, for the energies that we have in the daily world around us, the Dirac equation basically shows that we have a large component which is large and a small component that we should be able to treat perturbatively. And that's what I will like to do with you next in the next video, where we will go to the blackboard and start from the Dirac equation and see what the low energy limit is, and see that we can come back to the Schrödingerian equation and then see that we get additional correction terms to the Schrödingerian equations. And then we'll have a look at the size of these corrections. And I will not really show you experiments, but we'll have a look at a few of those sizes. And they agree very well with what we observe for the atomic states that we have in the world around you. For now, thank you very much for your attention, and we'll continue after the break on the blackboard to derive the low energy limit of the Dirac equation.